Hello, we're Team 1092 and our names are Matvey.
My name is Chukun.
And I'm Austin.
Our coach is Lena Feinman. We're students from College of San Mateo, and we will be sharing our solution to problem C of SCUDEM 2022. We will first start out by restating the problem provided to us, then share our basic assumptions and discuss the basic model that we will use. We will then show you how we modified the basic model in order for our solution to be more accurate. And then to conclude, we will share our solutions and analyze the results we got. The problem we have to solve has to do with the interaction between predators and prey and how humans that are introduced into an ecosystem affect the behavior that prey express. In the wild, with no humans in the picture, prey are engaged in behaviors that reduce the risk of predation. This behavior is what we call the anti-predator behavior throughout the presentation. We will explore how this behavior will change once the humans arrive and leave in the system of predators and prey. The basis of our model will be a basic predator-prey model, like I already said, where the growth rate of predators and prey is proportional to their population. The predator-prey model assumes that the growth rate of predators is dependent only on its natural growth rate and also food supply. On the other hand, the growth rate of prey is only dependent on its natural growth rate, but also its rate of predation. We also make an assumption that food supply and growth rate of predation is proportional to the product of population. And our final assumption for the basic model is that the environment does not change and all the parameters in the settings are constant. Here's the basic predator-prey model that we will use. Here we have dn over dt as the change in number of prey with respect to time, and dp over dt as the change in number of predators with respect to time. Change of number of prey equals to growth rate minus rate of predation. Change in the number of predators equals to growth rate minus decay rate from natural causes, for example. The solutions of the predator-prey model have the following form. Here we see the population of predators and prey throughout the time. Both predators and prey populations are periodic. Now, in order for the predator-prey model to work for us, we have to make certain assumptions, such as the environment's not constant as humans are entering and leaving the system. More specifically, the interaction between predators and prey is not constant due to those changes in anti-predator behavior of prey.
We modeled the change in anti-predator behavior according to previous research. Jeffroy et al. Found that human contact causes a loss of anti-predator behavior due to decreased predation risk and more contact with humans. It was also found that anti-predator behavior while in contact with humans is well modeled by exponential decay. We assumed that a loss in human contact has the reversed effect and an increase in anti-predator behavior. In order to add anti-predator behavior to our model, we introduce a function b of t, representing a normalized value of anti-predator traits exhibited in prey, where a value of 1 would be the amount of anti-predator traits exhibited by prey-human contact. B of t is then an equation of exponential decay, what humans are entering, and the reverse, what humans are leaving. Here are the graphs of B of t when humans are entering and leaving. The way we add behavior to our model is to multiply the inverse of the anti-predator behavior function to the predation rate and the predator's growth rate. We multiply predation rate by the inverse of B of t, the anti-predator behavior rate in prey, since B of t is inversely related to predation rate. For example, an increase in anti-predator behavior leads to a decrease in the rate of predation. Using the same reasoning, the growth of predators is also multiplied by the inverse of B of t.
To solve out this differential equation set and to get rid of the coefficient, we use scaling method. We make tau equals to at, u tau equals to c times nt over d, and v tau equals to b times pt over a, and alpha equals to d over a. Then the equation set becomes to du over d tau equals to u times 1 minus v over bt, and dv over d tau equals to alpha times v times u over bt minus 1. And here's our solutions.
Now, with the arrival of humans, the anti-predator behavior of prey will decrease since prey will be protected by humans. When the anti-predator behavior decreases, prey is more likely to be eaten upon encounter with predators, leading to a decrease in the population of prey.
Now, in the case of humans leaving, the the prey will regain their anti-predator behavior since the prey has lost humans' protection. So the anti-predator behavior will increase, which leads more prey to survive. Therefore, the amount of prey will increase. However, in reality, the amount of prey should increase when human arrives, and it should decrease when humans leave, which is not what we get from the analysis of our module. So, only considering anti-predator behavior is not accurate enough to model the question. We must consider the effect of humans.
When introducing a new factor, such as the amount of humans, we have to make certain assumptions. First, we assume the predators and prey are evenly distributed throughout the ecosystem. We also assume that humans enter linearly and eventually reach a constant amount of occupants. Same applies for when they leave. Humans leave linearly until there are 0 occupants left. We then also make an assumption that predators are not entering the area that humans reside in, while prey is allowed to roam around the humans' area. This should decrease the contact between predators and prey. Finally, the available prey is the product of the percentage of area that predators reside in and the number of prey.
In order to add the impact of humans, we construct a new function h of t, which represents the proportion of the ecosystem that is occupied by humans. Since we assume that predators cannot be in human-occupied area, the predator area function f of t is equal to 1 minus h of t. With the addition of humans, we also modify our assumptions about anti-predator behavior. Previous research shows that the degree of human contact matters. Animals experiencing different forms of human contact had different rates of decay. In our model, that means that the rate of decay of anti-predator behavior is dependent on human density. Therefore, that means that the derivative of the previous b of t is now multiplied by h of t. Since h of t is a piecewise function, the solution to b of t is also piecewise. In a similar manner, we also derive b of t when humans leave. Just like the previous model, the inverse of b of t is multiplied by the predation rate and growth rate. We also multiply predation rate and growth rate by the proportion of area that the
Using the scaling method we used earlier, we developed 2 graphs of the predator-prey model with anti-predator behavior and humans accounted for. Left graph is for the case when humans enter, and the right graph is for the case of humans leaving. In the case of humans entering, the amount of prey will at first increase rapidly since they have a safer environment. By that, we mean less encounters with predators and more protection by humans. However, as time goes on, prey exhibit less anti-predator behavior traits and become more vulnerable to predation, leading to a decline in the prey population. As time eventually goes to infinity, the amount of prey and predators will still be larger than the initial values.
In the case of humans leaving, the amount of prey will decrease rapidly. This happens because the prey lose their protection from humans, and they also lack the anti-predator behavior that is needed to keep them safe. Naturally, after a few years, prey will regain their anti-predator behavior, and gradually the amount of prey will increase. Since the anti-predator behavior has approached to 1 again, the final amount of prey is close to the original amount before humans arrive. However, we notice that some parameters lead to extinction when humans leave. For instance, when HF equals to 0.9, K equals to 1, the amount of prey will reach 0, which means the prey goes extinct. On the left graph, x-axis represents the speed of human exit, y-axis represents urbanization. The color represents the minimum value of the prey, ranging from blue to yellow, with lighter colors representing a lower minimum value. Yellow value represents a minimum value less than 0.01, which we consider as extinction. Here's our observation. If humans occupy a small area when they arrive, or occupy a large area and leave gradually, or occupy a small area and leave quickly, this will cause lower probability of extinction of the prey. If humans occupy too much area when they arrive, or occupy a large area and leave quickly, this will cause higher probability of extinction of the prey. So, Urbanization is more dominant than the speed of human exit for the minimum value of the prey.
In conclusion, human exits either cause predator and prey populations to go extinct or restore back to its pre-human dynamics. Effects of human on the ecosystem is dependent on the rate of human exit and degree of urbanization. In order to minimize risk of extinction, it is important for humans to gradually leave an area, giving prey time to redevelop their anti-predator traits. We found that removing the assumption that prey would be evenly distributed would drastically change our model. Our model also does not consider more lasting negative effects of human activity. Solutions to our model are continuous, while reality is discrete, which could make it hard to determine extinction. In the future, we'd like to model lasting environmental harms, model growth rate of prey as a function of anti-predator behavior, and use our model to model virus, immune system, and medicine interactions. These are the research that we used, and the Jeffroy et al. Paper was a part of the problem statement.